Okay, welcome back for this new session on the shaft. In this video, we will see how to derive the stiffness matrix of the shaft element. We already know the stiffness matrix. It is derived using the strain energy. What we have done, this stiffness matrix for the bar element, we are using the same method to find the stiffness matrix for the shaft element also. Okay, there is no change in the procedure. We will see some other method to derive the stiffness matrix now. Okay, by using this torsion equations, we already know this torsion equation: T by J equal to tau by R, that is equal to G theta by L, where shear stress, tau is the shear stress, and shear strain. What is shear strain? Strain, it is change in length to the original length, that is linear strain. Shear strain, it is the shear strain. Okay, see here, change in length, but here it is not change in length, it is angle of twist divided by original length. Original length, it is L. Okay, that what is the twist here? The point B changes to B dash. Okay, so how much is this change in this arc? Okay, it can be calculated by this arc, that is the radius is R and it is making angle pi. So the angle of arc, that is the change in this point, it can be calculated, that is r phi. Okay, r phi, that is the angular displacement. Okay, change in the displacement divided by original length, that is length. Okay, so this is shear strain and tau is the shear stress. Okay, we already know that linear stress divided by linear strain, that is equal to Young's modulus. But in the torsion of shaft, shear stress divided by shear strain, that is this nu, that is equal to modulus of rigidity. So shear stress can also be expressed as G into gamma, that is gamma means it is shear strain, G is modulus of rigidity, tau it is the shear stress. Okay, by this torsion equation, T by J equal to tau by R, T by J equal to tau by R. So what is the torque applied? Okay, T is equal to, it is if J into tau by R, this T can be expressed as tau by R into J. Okay, substituting this tau value is G into this gamma. Okay, substituting this gamma value, it is R pi divided by L. Okay, substituting all here, J by R is equal to tau, where tau is G into gamma. Gamma means R pi divided by L. Okay, this R and this R get cancelled, so it is Jg by L pi. Okay, what this is general equation to find the torque. Okay, what is the torque applied at the node 1 and node 2? The finite element formulation of this shaft, it is one noded element, sorry, two noded shaft element, where at node 1 the torsional moment is T1 and at node 2 it is T2. Okay, let us apply this equation to node 1. Jr by, what is left here, Jg by L into pi, Jg by L into pi into pi 1 minus pi 2. Okay, see here, this torque at 1, at node 1, Jg by L pi, pi is the angle of twist. Okay, pi 1 minus pi 2. Okay, this pi is mentioned as pi 1 minus pi 2. This pi 2, it is the effect of this T2, it is nullified here. What is the angle of twist at node 1? Okay, this pi 2, it is the effect of the T2, it is subtracted here. Okay, similarly T2, Jg by L pi 2 minus pi 1. Okay, the effect of this T1, it is nullified here. Okay, now we have two equations, T1 and T2, it is the torsional moment at node 1, torsional moment at the node 2. T1, T2, Jg by L, it is common for the both equations, so Jg by L it is taken out, and what pi 1, this is pi 1 and pi 2 are the nodal displacement or the angle of twist at node 1 and node 2. It is expressed in terms of a nodal displacement. So what is the coefficient of pi 1 in the first equation? That is 1. what is the coefficient of pi 2? It is -1. Similarly, in the second equation, the coefficient of pi 1 it is -1, coefficient of pi 2 it is 1. Okay, so this, for the given force or for the given applied moment, what is the nodal displacement? Okay, the relationship which build such a matrix is called as the stiffness matrix. It is the stiffness matrix for the shaft element, Jg by L, 1 minus 1 minus 1 1. Okay, it is similar to the stiffness matrix for the bar element, where it is Ae by L, 1 minus 1 minus 1 1. Okay, this is one method using the torsion equations. For the bar element, we have considered the strain energy equation. Not only for the bar element, we have already also used for the truss element, beam element. Okay, what is strain energy? Half of integration of sigma t epsilon into dv. For the 1D element, dv can be expressed as a into dx. Okay, you need to substitute sigma and epsilon. How it is derived for the bar element, where epsilon is equal to bq. B is the displacement, strain displacement matrix, and sigma is EBQ. dV is A into dx. What is dx? Le by 2 into d zeta. Okay, substituting all the values, when the nodal displacement values qt and q are removed, what you will get, that is the stiffness matrix. Okay, so what is B here? 1 by Le minus 1 1. So the transpose, it is 1 by Le. Now it is column matrix, minus 1 1. Okay, B matrix it is derived for the bar element. The same matrix can be used for the shaft element also. The analysis is same. B is equal to 1 by Le, minus 1 1. It is a row matrix, minus 1 1. The transpose, it is a column matrix. Okay, now substituting all the values, you will get k is equal to Gj by L, 1 minus 1 minus 1 1. Okay, the method which is similar to the stiffness matrix of the bar element. Okay, you refer the stiffness matrix for the bar element derivation. It is similar to that. Okay, so the stiffness matrix for the shaft element is Gj by L, 1 minus 1 minus 1 1. Okay, thank you.